Hello friends and my dear students. So as we have completed the first half of the balancing chapter, which is static balancing and dynamic balancing, now we are moving towards the reciprocating parts of that, because those two are the parts or the techniques of rotating balancing. So now we jumped into the reciprocating balancing, how we can solve the problems related with the reciprocating balancing. Because first of all we have to look after that, what do you understand by the rotating or reciprocating unbalance. So in this context I will you have to encounter these few questions: that why reciprocating mass unbalance is there, why such kind of unbalanced masses are there. This is just because of the mass of reciprocating parts. In your slider crank mechanism or in your engine, this is your piston. So as you can see, the inertia masses for this is F is equals to m into a mass of the reciprocating parts into the acceleration, which is r omega square cos theta plus cos 2 theta by n. And the second question is, who will ultimately suffer? So the whatever the effects will be there because of this unbalance, this will be encountered by the crankshaft. And what is the magnitude? Magnitude, as I have already discussed, this will be equals to F is equals to m into a, that is mass of reciprocating parts into the acceleration. And what is the direction of this force? This will be the line of motion of piston. Whether it causes any vibration, yes, because this is unbalanced force, so definitely it will cause some vibrations which need to be balanced. So if you will see the formula of this unbalanced force, which is mr omega square cos theta plus mr omega square cos 2 theta by n, then definitely there are two parts, which is primary forces and secondary forces. Means first part will be for the primary unbalanced reciprocating forces. So keep this thing in your mind, that this is primary unbalanced reciprocating force, which is mr omega square cos theta, and another part is mr omega square cos 2 theta by n. As you can see here from the magnitude only, n is the obliquity ratio. So as you can see here, the primary unbalanced forces are very much on the higher side of this secondary unbalanced force. This is bigger in the magnitude in comparison to secondary unbalanced forces. Means these are the 70 to 80% of the by fraction or by magnitude of reciprocating unbalance. So our target is to balance this primary unbalanced force first. And reciprocating unbalanced forces are constant in the direction and along the line of stroke of the piston, as I have already discussed in the above questions. But the every moment the changing the magnitude, that's why they create high vibration, because there is a component which is called as cos theta, and theta is a proportional to the time. So with the time respect, it will change the magnitude and it will create some high vibration. So these vibrations are called as transverse vibration, which you have to solve or which you have to balance with the help of balancing techniques. So now how we can balance it out? So for balancing this, what you can do for balancing this kind of problem, we have assumed that if there is a unbalanced force which is equals to the mr omega square at an angle theta, so then we can say that we have attached a mass b, of the same magnitude as the mass m of unbalanced force at the same angle theta. As you can see here, this theta is equals to this theta at the same angle theta, and as it is attached on the same crankshaft, so this is also rotating with the same angular velocity, which is omega square, and this is the radius of rotation, which is b. So the formula becomes for this balance force, which is equals to b into omega square cos theta. And if you will attach this balance mass at an angle theta, then definitely another component will come in the picture. So this bb omega square sine theta will give you the value of perpendicular force or perpendicular force caused because we have attached the balance mass at an angle theta. If this b into b, the product of balance mass and the radius of balance mass, is equals to the unbalanced mass, this is mass of reciprocating parts into the radius of rotation. If this product is equals to this, then definitely it will completely eliminate the vibrations or unbalanced force but it will give one more component, which is bb omega square sine theta, caused high vibration along the perpendicular line of stroke. As you can see here, this is a perpendicular line of action to the line of stroke of piston, which is 90 degree. So this will create another cause for the vibration. So thus now a fraction of transverse vibration is to be balanced by the balancing mass applied, so that we have to get a small component of bb omega square sine theta. Why we are balancing it partially? Because it will create another unbalanced force in the perpendicular line of action. So we are going to balance it partially instead of balancing it fully or completely. So we have not balanced the reciprocating masses completely. We will have to balance only partial or some fraction of that. So what will be the fraction? This fraction should be in between 0 to 1. So we have taken a factor c, which will be equals to CMR. So after balancing, you will get unbalanced forces along the line of stroke is mr omega square, which is your unbalanced force, and this much of amount of force you have balanced. If you will subtract, then you will get the remaining unbalanced force in the line of stroke. Along the line of stroke is the value is 1 minus c mr omega square cos theta. And similarly, there is another component which is perpendicular to the line of stroke, which is c mr omega square sine theta. Now these are the two components which you have to look after. Now we are moving towards the two-cylinder locomotive, which I will talk in the next topic, in the next lecture, that how we can solve the problems of two-cylinder locomotives, which are the adjacent or similar topic to your primary balancing, which we have studied till now. Thank you so much. Thank you.